Good evening, everybody. A continuation of our current series into the process design of a biodiesel production system. We had previously concluded a biodiesel production system that facilitated film production using the so-called subcritical transesterification process. Now, I felt that it was necessary for us to explore alternative biodiesel production pathways, because I kept on getting queries as to how alternative production pathways may influence the biodiesel model that we have now developed, right? Now, I'd like to reiterate that biodiesel can be produced via different ways, right? There are different methods to produce it. Now, essentially, the conventional pathways of biodiesel, also considered as the alkaline catalyzed pathway, involves a transesterification reaction that incorporates the triglyceride, in this case the triolein in our model, right, reacting with a methanol in the presence of an alcohol, right? So in this case, you catalyze the process. So moderate temperatures are required, less than 100 degrees required to facilitate the production of your films, right? Your films, your fatty acid methyl ester with a byproduct of glycerol. Now, this process, this pathway, is only possible when you have an oil that has a low amount of free fatty acid content. Free fatty acids, in other words, short chain fatty acids in the oil that do not lead to the production of side reactions or undertaking of side reactions to produce unwanted side products. Now, what do I mean? Now, if you have a scenario where the oil that you have contains a high content of these free fatty acids, in the presence of the catalyst, in this case the alkaline with the OH group, right, you have a side reaction. Now, this side reaction leads to the production of a salt of the acid, which we can call, it causes the oil produced to have this thick-like spongy look, right? It messes up with the viscosity of the oil. So you cannot use an alkaline transesterification process when the free fatty acid of the oil exceeds 0.5 weight percentage, right? So you need to be very, very small for you to use it. Now, typically this process, the transesterification process, is typically used because it is most convenient, right? All you need to do is to introduce an alkali catalyst, and it happens in relatively short times. We're talking 2 hours thereabout, right? Now, to bypass this, an alternative approach to produce biodiesel involves the use of an acid catalyst. In other words, you replace the alkali catalyst with an acid, with a protonator, right? Now, in this case, you do not have the same challenge regarding the formation of an unwanted side product, because it's all acids, right? However, the utilization of an acid catalyst may take a very long time. So you have the process going as much as 48 hours just to produce your fatty acid methyl esters, right? So, having said this, these are the conventional pathways. These are the conventional approaches to produce biodiesel, right? Now, another thing we need to understand is that the transesterification alkali process also requires the oil to be moisture free. So you can utilize it for more or less what I call high grade oils that do not have free fatty acid content because of the samponification or unwanted side reactions that I talked about, okay? And you shouldn't have moisture content, because the presence of this moisture content will lead to a hydrolysis of the oils to produce the fatty acids that we're trying to avoid, right? However, if we do not have such an oil, alternatively, we may utilize a subcritical scenario that does not have the same issues that we have just mentioned. What I mean is this, right? Typically, under subcritical conditions, if you have an oil that perhaps contains water or has a high fatty acid contents within it, you do not need an alkali, you do not need an acid catalyst. You just transesterify under high conditions of temperature and pressure. I discussed it at the beginning of the slide. I would like to refer us back to the first presentation where I described the subcritical transesterification process. So I won't be discussing that here. So I refer us back to the first class on the biodiesel production pathways. That was part 1 of the biodiesel series, where I discussed extensively the catalyst-free esterification process, and I utilized the paper that I had published previously, utilized the kinetic parameters from that paper to model the process, right? Alternatively, we could utilize a so-called hydroesterification biodiesel production process. Now you have a scenario where your oils already have a high free fatty acid content. So what do? You hydrolyze the oil even further to completely hydrolyze it to fatty acids, right? You hydrolyze it completely to fatty acids, then you esterify. Now this is just an approach that tries to bypass the need to introduce an alkali catalyst, right? So once you hydrolyze it, you get your fatty acids and your glycerol, right? Now this fatty acid is now esterified to produce the fatty acid methyl esters and water. Of course, the fatty acid esterification occurs under the action of an acid catalyst, but now it is faster because esterification is way faster than transesterification. So the esterification step may occur in less than two hours, right? It's typically a faster process. So a 48-hour process is made like a 2-hour process, right? But now it's 2 steps, right? So I want us to understand there are so many pathways to undertake with respect to biodiesel production. There are alternatives, right? Alternatively, you can also have supercritical hydroesterification processes, right? This may also be useful when you have a significant amount of moisture content in the oil. So you may choose to hydrolyze it first, then esterify, right? But because it's now catalyst free, under those conditions, very briefly, under the subcritical conditions, the characteristics of water change, right? I mentioned this in the first class. Now the characteristics of water change such that it begins to behave more like say a non-polar solvent. Like it becomes non-polar with a dielectric constant of like 20, right? So very similar to acetone. So the phase is changed, enabling the reactions between the oil and of course the alcohol, or in the case of the transesterification step, or the fatty acids and the alcohol to be more efficient, right? So please, I'll still refer us back to the biodiesel part 1 class to better understand what's going on. Now, what happens to the model that we have been able to develop? How does it change? Now, the first thing, if we are utilizing an alkali process, so an alkali catalyzed process, a transesterification process, we need to introduce a catalyst, somewhere in here. So first and foremost, what determines what biodiesel production step you are going to use? First, what is the grade of the oil? What is the quality of the oil that you have? Now, do you have an oil that has a lot of free fatty acids within it? Now, if you have a lot of oil that has a lot of free fatty acids within it, then that suggests that you cannot catalyze it using an alkali, right? So in that case, you may choose to catalyze it using an acid, bearing in mind that this process will take a very long time, right? So if we're using an acid catalyst, for instance, we introduce an acid catalyst to the system. Now you may choose to introduce a mixer, or you may choose to introduce the catalyst just before the mixer here, right? You introduce it before the mixer and the process goes on, right, all the way to the reactor, right? Now of course, if I introduce an acid catalyst, for instance H2SO4, you have to remove the catalyst at some points in the downstream after the reaction. Now recognize that the catalyst, all it does is that it enhances the rate of the reaction. In itself, it doesn't really change itself, right? It doesn't change its state. So it just enhances the catalyst, the rate of the reaction, to facilitate a faster one, right? So you should be able to remove the catalyst and the downstream by introducing a so-called neutralization step, right? So we're going to introduce, say, NOH to this step, right, or CaOH, so an alkali, right, to neutralize the acid to form a salt, right? So if we use CaOH, we're going to form a salt, right? In this case, CaOH, H2SO4 should produce what? CaSO4, right? So calcium sulfate, which is also called gypsum. Now it's insoluble, so it can easily be removed from the mixture, right? So you can remove it from the mix, right? So that's it. You need to understand first that there are several methods of producing biodiesel, right? The type of method or the pathway you use will depend on the type of oil, the quality of the oil that you have, the presence of moisture in the oil, right? Of course, the conventional and the traditional way of producing biodiesel is simply to transesterify the oil by reacting the oil, in this case the triglyceride, directly with an alcohol in the presence of an alkali or a base catalyst, right? However, this is only possible if the oil, right, has low free fatty acid content, less than 0.5 weight%, and has no moisture in it, right? So it's water free, right? Now if it has free fatty acid content in it, that will suggest that you will have unwanted side reactions occurring, leading to the formation of metallic salts of the fatty acid, the free fatty acids, right? The reaction is called the saponification reaction. This is an unwanted side reaction that we do not need, right? In other words, you may choose to utilize an acid catalyst as an alternative to a base catalyst, but we must recognize that the acid catalyst takes a very long time to attain completion. Now, in the presence of these limitations, the alternative is to use the catalyst-free subcritical transesterification process, or utilize the hydroesterification process, right? Hydroesterification process essentially hydrolyzing the oil first, right? Typically occurring at about 120 degrees. Now you hydrolyze it, you get your fatty acids, then you esterify. Now you can do this because the esterification step is always faster than the transesterification step when catalyzed with an acid catalyst, right? So you can split it into two steps, right? Now I will encourage us at this juncture to try to introduce the catalyst before the mixer, right? So decide for yourself. You're using a low grade, a high grade oil, right? You introduce the catalyst before the mixer, right? And introduce a reaction, a neutralization step just after the reaction step, right? To neutralize the acids, right? To form a metallic salt. Now, of course, you also need to introduce a separation step just before the purification steps involving the removal of methanol and the rest, right? So the purification step will involve the separation of the Giemsen from the mix. In other words, the calcium sulfate, right, from the mix. Right, so I look forward to the outcomes of this. I'll be looking at the comments down below. I just felt it was necessary for me to explain this based on the questions I was getting. There are different ways to get biodiesel. We expect that from the next class we will now explore possibilities of heat integration, right, in Aspen Plus, right? And of course, I also want to explain how to integrate Aspen with Excel, right? I didn't know this myself for a very long time, right? When I was exposed to it, it was quite helpful because this also helps with undertaking what if scenarios. What I mean is you need to change several factors. You don't need to keep running Aspen. You just change it on the integrated Excel file, right, and you run it from Excel.